This is a video from section 4.4 in linear algebra. Let's take a look at 19. Use the Wronskian to show the following sets of vectors are linearly independent. In part A, we have vectors 1x and e to the x. W of x is the determinant of, well, the first row will be 1x and e to the x. Those are the entries. In the second row, to get those entries, we take the derivative of each entry in the first row with respect to x. So in other words, the derivative of 1 with respect to x is 0, right? The derivative of x with respect to x is 1, and the derivative of e to the x with respect to x is e to the x. To get the third row, we take the derivative of each of the entries in the second row. And so we're going to get 0, 0, e to the x, right? And when we take that determinant, we get e to the x, which doesn't equal 0 for all x. And so what that tells me is the set containing the vectors 1x and e to the x is linearly independent. Part B. Suppose I'm given the vectors 1x and x squared. W of x is equal to the determinant of, remember we're looking at the Wronskian. This is the determinant of where the first row is 1x squared. The second row is 0, 1, 2x, right? I took the derivative of 1 with respect to x, the derivative of x with respect to x, the derivative of x squared with respect to x to get that second row. Taking the derivative again to get the third row, we get 0, 0, 2. When we take that determinant, we get 2, and that doesn't equal 0 for all x. And so therefore, the set containing vectors 1x and x squared is linearly independent. Let's take a look at 22. Show that for any vectors u, v, and w in a vector space V, the vectors u minus v, v minus w, and w minus u form a linearly dependent set. Remember, capital V is a vector space. It doesn't matter what three vectors you choose, we're going to get a linearly dependent set. So what we do is we set A times u minus v plus b times v minus w plus c times w minus u equal to 0. So can we find scalars a, b, and c that are not all 0 for this equation to be satisfied? That's the goal. So if we go to the second line, notice how au minus av plus bv minus bw plus cw minus cu equals the 0 vector. Now, I'm going to collect the u vectors together, the v vectors together, and the w vectors together on the third line. So I'm going to get au minus cu plus bv minus av plus cw minus bw equal to the 0 vector. And so remember, we live in a vector space. So if we go to the next line, we can say a minus c, that quantity times u, plus b minus a, that quantity times v, plus the quantity c minus b times w equals the 0 vector. Now notice, if a minus c equals 0, b minus a equals 0, and c minus b equals 0, this equation is satisfied, right? So that means a equals c, b equals a, and c equals b, right? So let me say that again. If a equals c, b equals a, and c equals b, this equation up here works. It's satisfied. And what that tells me is if A, B, and C are all the same number, the equation is satisfied. So all I have to do is let C equal to 1. And if C equals 1, then A and B are both 1. And so therefore, 1 times U minus V plus 1 times V minus W plus 1 times W minus U equals 0. So we found a linear combination of vectors U minus V, V minus W, and W minus U to equal the 0 vector, where not all of the scalars are 0. And so by definition, U minus V, this vector, V minus W, and W minus U form a linearly dependent set. Now, for the record, I could have let easily C equal 2. If C equals 2, then A and B are both 2, and I claim this still would be fine. You just need a combination where not all the scalars are 0. And I found one. And so, therefore, this set of vectors form a linearly dependent set. And that's how we do problem 22. Okay, that'll do it for this video for section 4.4. And we looked at problems 19 and 22. Okay, thank you.